Okay, so how is everyone today? Good, I hope? All right. So, a couple of minor issues here. So then, what's today? The 26th, yeah. So then, concerning Wexes. In the first place, we said, well, the exam's going to go up to 05, and then we said, nah, 07. And then I graded your quizzes, and I think, nah, let's make it 05. Because in the end, many of you, the responses that I saw from this section and the other section were really concerning. So then I think probably the best thing we can do today is review for the exam, so that's what we're going to do. So we're, finally, there'll be no other change here. The midterm is going to be up to WEX 05 series, and we will still, you can redo up to 7. Why not? It's been up to 7. Of these ones. Okay, good. Also, so concerning just for the review now. The first thing I want to discuss. So, any questions about this? This is okay. All right. Concerning the material for the redo, let's consider. Not for the redo, but for the midterm review. Let's consider. What if we have, say, the following function? If we write f of x is, say, half x minus 3, say, then it's just expected that you should know exactly how this function appears. So that's just expected. So in particular, if you were to plot this, how would it appear?
Like a lazy linear function that starts at 0.
Okay, very good. So you just have to know, it's presumed knowledge, that when you look at something that that matches the format y is mx plus b, then such a thing is a line with slope m and y-intercept 0b. So in particular, that means that the plot of y is f of x will be a line with slope half. And y-intercept 0, negative 3. All right. So we could make a sketch, just a quick sketch of how this appears. So the y-intercept is telling us that this here must be one of the points. 0, negative 3. And then from there, I like the way you characterize it, sort of lazily sloping up, which is to say that, well, for every 2 units you move to the right, what? You do 1 unit up. That's what it means for the slope to be 1 over 2. So then, you know, maybe more or less like this. So that's just assumed knowledge. And another bit of just assumed knowledge is that concerning these M versus B, is that if M, so the first column will be M less than 0, and well, I guess I'll make it to have 3 columns. Why not? M less than 0, M equals 0, and M greater than 0. And I think just probably 2 rows is enough. So B less than 0, B more than 0. All right. So then when M is less than 0, such lines are said to be sloping how? Fishing for a D word. Down. Yeah. So they slope down. Or if you like, they slope negatively. So drawing a little axis in here. In each one of these. So these will be sloping down. So what is B less than 0? What is that going to signify? Right? And so what will that signify visually for everything in this row? Okay, very good. Sort of on the bottom half, right? So that means that the line must go through the vertical axis, but it must do so below the origin. So this means below the origin. And this one means above the origin. So that means that all of these will be like this somehow, more or less, and all of these will be like this somehow, more or less. Okay, so then to be in this column means that we are going to slope down, or negatively, if you like. What about in the rightmost column? What's that going to mean? That means that the slope is going to be up, so, or if you like, positively. And then what is it going to mean to be in the middle column? Horizontal. So, again, mathematicians sort of have a, I mean, I know what you mean by flat, but mathematicians have a special meaning for flat. Like, for example, that screen is flat. Well, I mean, me too is what I, in the end, is what I mean. So, for these ones, everything in this column will be sloping down. So these will kind of go like this. Slope down somehow. Everything in this column will be horizontal, like so. And then everything in the right column sloping up. And we didn't draw it, but I think you could probably imagine the one case of b that we didn't consider was b equals 0. And what does that mean? Yeah, so we considered b less than 0, we considered b more than 0. What about the specific case b equals 0? It means that green point would be exactly on the origin, right? So the line itself would pass through the origin. All right, good. So this is just presumed knowledge. Second, what if we have a function that so I don't have enough room on this page, so I'm going to just say next page, but it's a continuation of this example. So this is 2. So what if we have a function like h of x is equal to, say, half x minus 3 when, let's say, I don't know, x less than 3, and it's equal to, how about, say, negative 2 otherwise. So a function given in this style, this kind of style, is called piecewise defined. So h is piecewise defined. It might help a little bit when considering these to know the jargon. So each one of these rows is called a clause. So clause. The clauses are usually numbered from top to bottom, starting with 1. What each one of these things right here, these are the conditions that say when a particular clause is going to be used. So these conditions collectively, right here, these are called the guards. And these ones right here, which tell you what to do, these are called the formulas. So, you know, you can say unambiguously that that's guard 1, and that's formula 1, and that's guard 2, and that's formula 2, etc. So, when you're doing this, for example, I could say, please evaluate h at, say, 1. Well, how do we do this? So how do we, what are we supposed to do here? Integrals? There's no integrals yet. We're not even talking about integrals yet. all I'm asking about is what if you wanted to plug in 1? That's all I'm asking. Okay, good. So the question in the end is that you consider the guards, which tell you when are you supposed to do what. All right. So then, so a function is a thing, and a number is a thing, and you know, sort of conceptually, a function's like a machine with inputs, and the input is 1, and the name for the thing that you put in the other thing, the math name for that is argument. So what you need to do is you can consider, okay, the argument currently, what's being discussed, is 1. So the question is which guard satisfies this? The first one, right? The first one because, well, what we're doing is that we come over here and we ask, which one of these guards is true? And it's this one. We're going to use we're going to use clause 1 in the end because 1 less than 3 is true. All right. So then, in order to evaluate this, we'll use clause number 1. And then plugging that in, we plug in 1, so that'd be half times 1 minus 3. So that'd be half minus 3, so negative 2.5. All right. What if we're asked about, how about h of negative 8? What clause will we use? The first one again, right? Because in the end, the argument is negative 8, and negative 8 less than 3 is true. So then we're supposed to do that one. So again, to evaluate 8, the h at negative 8, we'll use clause 1. And the result will be half multiplied by negative 8 subtract 3. So that'd be negative 4 minus 3 is negative 7. Okay, good. How about h evaluated at, say, 10? So what will that one be? It'll be guard 2. The reason is because now the argument, the input to the function is 10. So now we're going to come over here, and in the end we're going to do this because, well, let's consider what's being said. So we're going to do that one because, well, consider the inequality 10 less than 3. So is that true or false? That's false. So the clauses are evaluated top to bottom, which means that, well, we let that one have the first stab at it, and it wasn't true. So it's not that one. And then we come to that one, and otherwise means that, oh, this is like the catch-all. If nothing above was true, then it's always going to be this one. So because 10 less than 3 is false, so then that one catches everything. Okay, so as a result, we'll use clause 2 to evaluate that. So the answer is going to be negative 2. Any question about that? Okay, what about h evaluated at 3? The second one, right? It's not the first one. Why not the first one? Right, because, well, consider the statement. 3 less than 3. Is that true? It's not true. So then we'll again use the second clause. And therefore the output is negative 2. All right, good. So now I have a question. What is the domain of h? That is to say, what inputs are permitted, and furthermore, which inputs go to which clause. All right, so let's think of an example, like for example, square root of x. Are all inputs permitted for square root of x? No, not all of them, right? So for example, you can't input a negative number. All right. So in particular, what I want you to see is that these piecewise defined functions sort of have the flavor that they sort of, because there's two clauses, this function sort of has 2 lives. And its life changes, sort of at the places where these two join, where they meet up. And you can see that there's a join occurring at 3. So add x is 3 there. So that's where the function sort of changes its mind. What clause holds sway to the left of 3? The first one, right? So clause 1 is the one that holds sway over there. And then the second clause everywhere else. All right. So now concerning open and closed circles, suppose that I refer to this one as the red clause, clause 1, just for visual sake. I want to color in what part of the domain corresponds to clause 1. So all of this corresponds to clause 1. It's all clause 1 there. But a question arises is that what about exactly at 3? An open circle, right? So open, because that signifies that that's not part of it, right? Okay, good. That's what behavior clause 1. And then clause 2 handles everything over here. But again, we have the question of what about exactly at the join point? Does green fill it in, or does it leave it open? So calling this one the green clause. So does the second clause fill it in or not? Well, it does, right? Because that's what we just said there. We said that what if you plug in 3? Well, you're supposed to use the second clause then, right? Well, because I haven't filled it in yet. I'm just asking. Am I supposed to fill it in? And the answer, okay, good, is yes. Good. Filled in the end, you know, you can see it from like right here, say. So as a result, you know, if we were to write this domain in interval notation, you could say that the domain is negative infinity to 3 with open parentheses, and then union, square parentheses, 3 to infinity. Now, before you ask an obvious question, I'm going to ask a different question and say, what is the meaning of that open parentheses and square parentheses? What do those mean? Can you remind me? Right. So it signifies inclusion, right? So just looking at that, is 3 included in that set? No. Just looking at that one, is 3 included in that set? Yes? And so now the question that you want to ask, go ahead.
Why is it not from negative infinity to infinity?
Of course it is, right? So what I want you to see is that this expression, right? This is the union of the domains of the individual clauses. This is the domain of clause 1, union, the domain of clause 2, and do you observe that in fact no point whatsoever is left out of consideration? So as a result, this union of intervals simplifies to this, meaning that in fact nothing was left out. All right? Suppose I want you to make a sketch of H. Well, to understand how to make a sketch of H, I'd like for you to see the sort of like the idea of how this works. What's happening is that this function sort of, again, like we said, it's defined everywhere, and it changes its mind how it's going to be at that input. Clause 1 holds sway on the left side, and clause 2 on the right. So now I'm going to draw something. It's not going to be right. I just want you to get the general idea about what must occur, and that is that you know, if we were over here, and we were just a little bitty creature, we were right there, and we're so far away from this fence that we can't even see it. Right? We're nowhere near it. Then that would mean that to us, the formula for the world would look like half x minus 3. You know, if we're so far away from that fence that we can't even see it. Well, on the previous page we said what half x minus 3 is when you plot it. It's a line that slopes lazily upward. So that means that to the left of this join, what's happening is that we should be a line that slopes up somehow. And again, I'm not trying to make the slope right, I'm not trying to make the intercept right, I just want you to get the general idea that over here we're sloping up. So when we meet the join, right there at 3, will it join open or closed? Open, right? Signifying that there is in fact not a red point right there. All right? Then, if instead of being right there, if instead we were right here, but again, we were a little bitty creature and we were so small and so far away from that join that we couldn't possibly see that, we couldn't even see it, it's so far away, then the formula for the world would look like that, h of x equal -2. So what does the plot of y equal -2 look like? Horizontal line, right? The horizontal line. Again, I'm not trying to get the formula exactly, the sketch exactly right, just the general idea. So it would be some kind of horizontal line, like this. And when we come to the join, will we join open or closed? Closed. All right. That's just the general idea. So it's you know, going to be a sketch. It's going to look like the function changes its mind from red behavior to green behavior. Now let's make it right. Let's get it exactly right. An actual sketch. So I'll do it right here. All right, so I can see that there's a joining point at 3, so that must be significant, so I'll draw it. So there at x is 3. Okay. The behavior on the right side is a little easier to look at, so I'll do it first. So I need to draw a horizontal line, and it needs to join closed, and in particular the height is at -2. All right, so then it'll look like this. So it looks like that. And then now, on the left side, what we want to do is just, again, plot some points. So let's figure it out. So again, on the previous page, we discussed that y equal half x minus 3. That's a line with y-intercept -3 and slope half. So that means that here we can start at -3. And then the slope being half means that, what does that mean? How can we plot a next point relatively easily? Besides like plugging stuff in, I mean.
One to the right, half up, or two to the right, one up.
Okay, good. Either one of those are the same. Very good. So I'll go over 2 and up 1, so that's a point. Now, if I were to go over 2 and up 1 again, I'd cross the join, so I can't do that. So I'll go to the left a little bit. So there and there. So like this. So like that. So now, here's one of the reasons why I'm asking about this one, considering this specific question. is that I asked, for more or less, one of the tasks of one of the exercises was to sketch something not so different than this. And many of you responded with something like this. So this is just not right. So what's wrong about this?
It's just missing the points between the two.
What do you mean between?
Right there where the finger is between, I guess, 2 and -2.
Well, I mean, you know, well, let me ask it like this. If I plug in 3, the actual join value, do I use the red clause? If I plug in 3, I don't use it. So is there a point there to plot? I mean, so let's consider, because there's an issue here that comes up a lot. So let's ignore the picture for a moment. Let's ignore that for a moment. And I want to ask, how about, say, so I asked these evaluations already. What about like h evaluated at 2.5? So in the first place, is it permissible even to plug in 2.5? Is 2.5 like a number? Yeah, 2.5 is a number, right? So then the input is 2.5. The argument is 2.5. Which clause matches? The first one, right? Because in fact 2.5 is less than 3, right? All right. So then we would evaluate the first clause. And then the formula we'd use is half the input, and then subtract 3. So half of that is what? 1.25, and then minus 3 is what? Negative 1.75. All right. So that means that there should be a point there. So now here's the thing. What I want you to observe about this picture is that the meaning of this picture, the way it's drawn, I could ask, well, for example, exactly at x is 3, is there an intersection? There is, right? The green one is intersecting. That means that 3 is in the domain. And if I come to like right there, which is for 4.5 right there, is 4.5 in the domain? It is, because there's a green intersection. Similarly, if I come over here, say to x is -2, is x equal -2 in the domain? It is, because there's a red intersection. There's a red point right there. Now, the way that the picture is drawn now, at 2.5, is there an intersection at 2.5? The way it's drawn currently? There is not, right? There's not a green one, because it ends there. There's not a red one, because the way it's currently drawn, it ends there. So this kind of mistake comes up a lot, and it came up a lot last week, actually. In the end, what I suspect is that, well, we're humans, and to us, integers are beloved, and they really are. And I make no dispute, there are, in fact, no integers between 2 and 3. There aren't any to be had. But are there any other numbers to be had? Yeah. Yeah, there's a bunch of them in there, right? Infinitely many, right? So as a result, this continues all the way to here and then joins it with an open circle like that. So that little bit there was missing from a great many students' responses. I suspect, I mean, I can't read minds or anything, but I suspect in the end the problem is that lost sight of the fact that there are numbers in between 2 and 3, even though there aren't any integers between 2 and 3. Good. Any question about this?
So, in order to find that to make it accurate,
Yeah?
we're best plugging in, like in clause 2,
Mm-hmm.
like a number between clause 2, or a number that's still
Well,
close to
specifically,
start and
Yeah, you could think of it like that. Now, I could say, well, for clause 1, in fact, are you supposed to plug in 3 for clause 1? You're not, right, because it says no. But if we suspend that for a moment and just imagine, well, suppose we do it anyhow. If we plugged 3 into there, right, then we'd have half of 3 minus 3. Right, so that'd be negative 1 1/2. So draw an open circle at negative 1 1/2, because that's where it would have been, right? That's where it would have been. Otherwise, if that disturbs you, you can just draw a bunch of little blah, 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 blah. Or you can remember that the slope is half and do as he said and say, well, you could go over 1 unit and then up half a unit from there. So over 1, up half. A variety of ways. Any question about this? Okay, good. So let's do another one. I'm sorry?
Can I ask a question on what the boundaries on the
I'd rather, well, I'll agree to this. I'll agree, you ask the question, and then if I think that the video key handles it, then I'll just say, just see the key. So what's your question?
the one where we were given the radius of the circle.
Yeah?
And we have to find the shaded area of the circle piece.
Uh-huh.
Was the hint, like...
Oh, that one that says easy as pi or whatever?
Yes.
Okay, so then just real quick for that one. In the end, if you look at that carefully, so in the first place, well, if this is exactly a circle of radius r, and suppose that I made it exactly perfect, you can only draw so good. Then this is radius r, which means that this point here, that would be the point r, 0. This would be the point 0, r, going around, right? And so you can imagine that in principle, maybe not exactly, but more or less, you could take a pizza that was perfectly circular and cut exactly rent, and then each one would have 1/4 of the area, right? All right. Suppose that we go further, and instead of just that cut and that cut, suppose that we do a full pizza cut, which is to say that we cut half that one and half that one. And this is like a hypothetically ideal situation.
That was actually my question is, if we get one where the slope of the line is not 1?
I would never give you one like that.
Okay, that was my question.
So for this one, can we agree, supposing that, supposing I could cut perfectly, that each one of these pieces constitutes exactly 1/8 of the area? So the area of that would be, the area of the whole shebang, right, the whole thing, is pi r squared, which is assumed knowledge, and the area of that one piece there is would be the area of the whole thing, pi r squared, and then divided by 8. So for the specific question, that exercise, the situation was exactly that, except what I did is I said something like the following. I said let f of x be the following piecewise defined function. F of x is exactly x when 0 is less or equal to x is less than 3 over the square root of 2, like so. And then it's equal to the square root of 9 minus x squared from 3 over the square root of 2 less or equal x less than or equal 3, like so. So it was, you know, I can't remember exactly, but this less or equal either needed to be there or there. But that's not, that's kind of a minor thing. At any rate, what you need to know in order to answer the question, the request was for you to integrate 0 to 3 f of x dx. And of course, you had been primed to understand that you break the integration into pieces in correspondence to the number of clauses. So you might kind of try and say, oh, well, I'll try and break it into pieces, right, that one and that one. But I had also said that we don't have the ability to integrate the circle, at least not in this class, because we don't talk about trig functions. So the way this function works right here is that you know, you have to know two things in advance. Is that ignoring the fact that this is a piecewise defined function in advance, you have to know that the plot of y equal x is this, which is to say, what if it was only the first clause, unrestricted? You've got to know that. And then the plot of y equal the square root of 9 minus x squared is that, supposing that it was only the second clause with no restriction on the domain. So you've got to know those things, and then combining those two together, the picture looks like this. So there's x is 0 there. That's one of the fences. And then x is 3/2. Not 3/2. 3 over the square root of 2. And then 3 is the other fence. So that's like right here-ish. Combining these, and again, calling this clause 1 and this one clause 2, well, I have a question. So what clause holds sway to the left of x is equal to 0? To its left. So like, what I mean is like, for example, what about x equal to -5? What clause would you use? So, right, so specifically, I want to ask. So like, what if I ask, what about f of, say, in the first place, let's get the calculator here, because we've got to know about how big is 3 over the square root of 2. So 3 over the square root of 2 is about 2.1 there. So taking into knowledge that square 3 over the square root of 2 starts with 2.12 ... Then what about f of 1? What if we wanted to plug in 1? Which clause would we use? We'd use the first clause, right? Because if that's about 2.12, then 1 is between 0 and 2.12. So we'd use the first clause. And in that case, the output is the same as the input, so the answer would be 1. So now, what if we plugged in, say, 2.5? Then which clause would we use? The second one, right? Because if that's if square root of 3 over 2 is about 2.12, then this one is saying, you know, between 2.12-ish and 3, we're supposed to do that. All right. So then we could do that using clause 2. Square root of 9 minus 2.5 squared would be 6.25. You know, but the square root of that is anyone's guess. So 9 minus 6.25. Like that. My calculator says that that's about 1.66. All right. Then my question is well, what about, well, what if we wanted to plug in like -4? What's the correct response to the request, f of -4? Yeah, this is undefined. Because, well, let's ask, is it defined by the first clause? No, because -4 is not between 0 and 2.12-ish. Is it defined by the second clause? No, because, again, -4 is not between those two numbers. And there are no other clauses. So as a result, this is undefined. And for that matter, how about f evaluated at 8? I should say is undefined. Again, that's undefined. So what I want you to see is that there's four pieces, right? There's that piece, that piece, that piece, and that piece. There's 4 pieces, but only 2 of them have a definition. Just the middle 2. The leftmost piece and the rightmost piece do not have a definition. All right? So in this piece, which clause holds sway? The first one does. Okay, and over here is just undefined. And over here is just undefined. And how about in that bit right there? The second clause, right? So the second clause there. So that means that between these 2 joins, I need to draw the red thing. So I draw the red thing. Does that need to be open or closed or what? Open. Open because that says less. All right? Then, now I want to draw the green thing. Well, as it happens, what do you get if you plug in f of 3 over the square root of 2? What do you get? Yeah, so what you get is this is the square root of 9 minus 3 over the square root of 2 squared, like so. All right, then we need to square that, so that would be equal to the square root of 9 minus, well, the square distributes to the numerator and the denominator. What's the numerator squared? That'd be 9. And what's the denominator squared? 2, right? Because the square root of 2 squared is 2. So this would be equal to the square root of 9/2. And then now we can distribute the radical to numerator and denominator. What's the square root of the numerator? 3. And, well, the denominator doesn't simplify. It's just the square root. So I'll just write square root of 2. So those are the same. But what height is that?
What happened to the 9?
What happened to what?
9 minus 9.
Well, this is 18/2. What do you get if you take half of 9 away from 9? Half of 9, right?
I don't get how to get from the square root of 9 minus 9 to the square root of 9.
Okay. So maybe we can do an intermediate cross-multiply step. So if we were to cross-multiply, considering this to be 9 over 1, this would be 9 multiplied by 2 minus 9 multiplied by 1 over 2 multiplied by 1, right? So doing the cross multiply thing, so that'd be 18 minus 9 is 9 over 2. What do you what do you get if you take 10 and you take away half a 10? Right, which is half a 10. What if I give you 7 and you take away half a 7? How much is left? Which is half a 7. What if I give you 1326 and you take away half of 1326? How much do you have? Half of 1326, right? Whatever it is, right? What I'm saying is that the only thing that matters is that that and that are the same. We've got a full 9 and a half a 9. You take away half of it, and half's still left, right? Yeah, okay. So that means that, if you carefully work this out, that means that, in fact, there's a green point right here, filling in that dot. And then what is f evaluated at 3? Well, if you plug in 3, it'd be 9 minus 3 squared. So 9 minus 9 will be 0. So there's a green point right here. And then it's a circle arc of radius 3 between those. So it's like this. And if I was a perfect artist, then that, in fact, would be exactly 1/8 of a circle. So the point of this exercise was for you to consider the thing and come to the realization that, the question is about the integral of this function. Now, if I wanted to use the fundamental theorem of calculus, the fundamental theorem of calculus would say that, in fact, you need to split this into two integrals, so 0 to 3 of f of x dx, and then you'd have to go 0 to 3 halves, 3 over square root of 2, I mean to say, and you integrate the first clause, which means that, that's the red contribution, and then to that you add 3 over, the integral from 3 over square root of 2 to 3, and you integrate this, 9 minus x squared dx. That would be the green contribution, if you were to try to do the FTC. But the thing is that in our class, we don't know how to do that. So what I wanted you to come to realize is that, we don't know how to do this. We don't know how to use the fundamental theorem of calculus. We don't know how to compute the antiderivative of this. Nevertheless, we can still answer the question. We can still answer the question because, after all, the connection is that integral is area. Okay, so then in our class, we can't do this one. At least not an antiderivative. But the point is to make sure that you understand that, in fact, that's not necessary, because this is a perfectly reasonable part of a circle. So the purpose of the question is to emphasize the connection between area and integral. Any question about this one? So this dovetailed kind of nicely, because that's why I just went with it, because we're doing these piecewise defined things. Any question about it? Okay, one other thing I want to consider is, let's see, what time is it? 25, yeah, plenty of time. All right, so let's consider this one. How about, say, Q of W is defined in the following way. So like -2, when when W is less than, say, -3. And how about W squared minus 3 when, how about -1 is less than W is less or equal to 2, and W minus 5 when W is greater than 2. Okay, so then an interesting looking thing there. The first question I want to address is that what is the domain? Domain. Of Q. All right, and when you're considering this, something might seem a little bit odd, but I've intended to do this. So I'll give you a second to come to the place where your consideration finds it to be odd. So please consider it for a moment. Okay. Uh-huh. Okay, good. So again, taking the usual convention of numbering the clauses top to bottom, starting with 1, and referring to them as clause 1, 2, 3. Then, well, one pretty good strategy, especially for this particular one, is just to draw the whole reals there, and then also to draw all of the joins. So one of the joins here, which is to say the boundary of one of the guards, is -3. So I'm going to draw that one. So -3. What's another one? -1. Another? 2. Another? That's it. There aren't any others, right? You got to know when to stop. That's it. So now we've sort of carved the thing there into 4 pieces, and now we want to figure out which clauses hold sway over which pieces. All right. So color coding them, referring to this one as the red clause. So just like we number these in increasing order of 1, 2, 3. In case you haven't noticed, usually when I'm coloring something, I color them in color order also, right? So like the first color I start with is red. And then the next one I use is green. And then the next one I use is blue because that's the rainbow order, right? So calling that one red. Which, in the leftmost region, which clause holds sway? So it's got to be clause 1, 2, or 3 in the leftmost region. Clause 1, right? Clause 1 is what controls the destiny there. What about in this region? Is that okay? Yeah. Yeah. You might find that a little bit disturbing, but there's nothing wrong with that. So there's just none. What about in this region? Second clause? And in the right most? The third clause. So, you might find it odd that there's nothing there, but, well, consider the square root, for example. There's literally nothing at all on the left side. It's just not there. Okay, fine. So then, now, again, taking well, let's consider just the domain. So the domain for the red one, everything over here is included, so this is all included. And then the question is that when we come up to the join, do we join it open or closed? Open, right? Because it says less than. Now, if I, instead of writing less than, if I had written less or equal, then it would be closed. But it says less than, so this is open. All right? Then, all right, there's nothing in there, so we don't need to do anything. For this one, the green clause, all the stuff between these two fences is included, but the question of the boundaries needs to be addressed. So how about the left boundary? Is it included or not? It is not, right? Because that says less than. So this side is open. Okay. Then how about the right endpoint? It is included. So this one is solid. All right. Finally, then the right includes all of this. But then the question is what about exactly at 2? It's open, right? So, just to sort of help myself, I'll draw that. No, I don't insist on that. I'm trying to explain something that didn't seem to be clear from the homework. That is, so we could write this domain in interval notation as -infinity to -3, and then union all the individual pieces. So union -1 to 2, and then square parentheses on that, indicating that it is included. And then union, open parentheses on that one, to infinity. Now, this can be algebraically simplified. How can this be simplified? Mm-hmm. Okay, so you're telling me that, I think, it sounds like, you're saying that I could write it like this, -infinity to -3, and then union -1 to infinity, like so. And it sounds as if you are telling me that that's because this simplifies to this.
What about 2? Because I can break this way, parentheses.
Mm-hmm.
So how can you do like
Well, union just means everything that's in either one. So is 2 in that set? Just in that one. Is 2 in that set? All right. So then, how about is 2 in that set? It is. Therefore, because 2 is in the left set, it's in the union of them. Right? So that simplifies like that. Now, can we also simplify this to -infinity to infinity, say? No? But we made this one -1 to infinity. How come now we don't do -infinity to infinity?
Oh, because there's a chunk between -3
Yeah, because that big old bite right there, it's not there. Visually, the reason why this simplification is possible is because, well, the question is that considering this, were there any points missing? No, there were no points missing. There were no points missing whatsoever. And as a result, that simplification can occur. But no simplification here can occur, because that would be saying that I'm just going to ignore that gap. But it really is there. Okay. Good. Fine. So now let's make an idea for the sketch. So I'm going to kind of go through this part quick, because there's some other things I want to say, not related to this, or not directly related to this. So again, this is just the idea of what's going to happen. So then, if we were to plot this one, that's a horizontal line, the red one. So it's a horizontal line over here, and it joins open. There's nothing at all in there, so nothing. Between -1 and 2, it's a, well, what kind of thing is that, if you were to plot it? Parabola, right? So then, this is the blue clause. So then parabola, and then, so I'll just draw it like this. So open on one side, closed on the other, parabola in between. You know, this isn't a sketch. This is just the idea of what's going to happen. And then the rightmost one, if you were to plot that, how would it look? W minus 5. So what I'm saying is that suppose that we have, you know, some variable, so q of w. So we could say this is what the plot of like p is q of w looks like. Well, no, let's say it like this. This is the plot of what p is -2 looks like. So a horizontal line. This one is what the plot of p is w squared minus 3. So that's what that one looks like. Parabola. And then my question is what about p is w minus 5? What would that look like? A line. So at the join it would be open, and then it's a line that slopes up. So this would be p is w minus 5. Now I'm not claiming that it looks like that. I'm just saying that generally there's 4 phases of life to this function, you might say. The phase where it's going to be a horizontal line, the phase where it refuses to exist at all, the phase where it's going to be like a parabola, and the phase where it's like a line. So then from here you could, you know, you could go on to make a detailed sketch about it. So I'm going to do that real quick because I want to emphasize something that appears to be missed. On the homework, so the joins are at -3, -1, and 2. So -3. -1. And 2. And so now it's just a matter of sort of carefully translating that idea to over here. So then it's going to be a horizontal line in the leftmost region, and then the height is at -2. So it'll look like this. So it's open here. And like so. Between -3 and -1, there's nothing. So there's just nothing to be had there. Between -1 and 2, it's a parabola. But now we're plotting it, so we want to get the values right. So that means that, well, in the first place, because of the guard, is it permissible to plug in -1 into the second clause? You're not supposed to, right? Because it, you know, it's supposed to be not including negative 1. But let's imagine for a moment that we did. If we plug negative 1 in, then into that expression right there, w squared minus 3, what would we get? Well, we'd get negative 2, right? Because negative 1, you square it, that gives you 1, and then subtract 3, that gives you negative 2. So what does that mean? That we should, how does that translate to over here? It's an open circle, right? So then an open circle right there at negative 1, negative 2. So now, what if we plug in 0? Which clause for 0? The second. And then if you actually do plug in 0, you get negative 3. And then the rest I'll just do quick. If you plug in 1, you get that value. And if you plug in 2, you get 1. So that's this value. So then the green looks like this. All right. Then now, for the third clause, is it permissible? Is it permissible for you to plug in 2 into the third clause? No, right? You're supposed to plug 2 into the second clause. Suspending that for a moment, suppose we do it anyway. If we plugged 2 into there, what would we get? Negative 3. So how does that translate over to the plot? An open circle, right? So that means right here, there's an open circle. And then from here, we proceed like a line with slope 1. So for example, if we plug in 3, then we get negative 2. So right there, yeah, here, etc. Here, like that. Good. Any question about this one?
On the
Yeah?
closed plot for back to the parabola on 2.
That one?
Yes.
Yeah?
You came across that. You plugged in and
2
plugged in
into the second clause.
2. Okay.
That'd be 4 minus 3 is 1.
Okay.
Okay, so then that's what the thing looks like. So any question about it? Yeah?
If we were taking midterm or something, the lines with the function definition values, are those part of the diagram?
These things?
Yes.
No, you don't have to draw those. I just do that because I find that minimizes the errors on my part when I'm carrying out the procedure. Now, suppose that I say, now here's a plot. Here's a plot. I want you to plot the absolute value of this. All right. So now please plot P is the absolute value of Q of W. Again, where this is, you know, that says Y, but that's really P, and this is really W. So what this is the plot of Y is, no, not Y, because we're using the variable P. This is the plot of P is Q of W. And now what I'm saying is, well, suppose that we make it absolute value of Q of W. Then the question is how are these things related or different or what have you? So, making another one of these. Now, what absolute value does is whatever number you provide as input to absolute value, the output is either exactly that number or it's the negation of that number, which is to say, for example, the absolute value of 8 is 8, right? It just passes through the absolute value unchanged. But what's the absolute value of negative 7? 7, right? So specifically, you could say it as negative 7, because that's, you know, it negates it. As a result, what absolute value is going to do to the function is because P is the set of outputs and W the set of inputs, what this is doing is this is applying absolute value to all the outputs. So that means that at the present time in this picture, are there any negative outputs? Yeah, all the ones that are below the axis are negative. So for example, that output is -1. That output is -2. That output there is -3. So there's several negative outputs. Are there any positive outputs? Yeah, so for example, that output there is +1. That output is +2. So all of the positive outputs will pass through unchanged. All the negative outputs will be negated to their positive counterpart. So for example, that output is -2. When absolute value does its thing, it's going to become what? +2. So as a result, what happens is that to do this properly, we can again draw these fence posts. So there's a join here at -3. Another one at -1. Another one at 2. Okay, so those are the 3. But there's actually 2 more for this particular drawing. There's actually 2 more points that are significant for the purpose of drawing absolute value. Can you see what they are? Well, let's consider. If we were a little bitty creature and that was our whole world, that's all that we could possibly see, would absolute value affect us? It wouldn't, right? It would it'd have no effect. But, you know, if that was our world and that's all that we could see, would absolute value affect us? It sure would, right? So what we need to do is we need to also carefully mark the places where absolute value's effect becomes marked. Right? So specifically, you can see that there's a crossing right there and also right there. So those points also are significant. So this point, right there, that's going to be significant occurrence. And also this one that's just to the left of -2. So now I'm going to draw the things that absolute value doesn't affect. So absolute value doesn't affect any of this. So that's unchanged. Is there any other bit that absolute value is not going to affect? Yeah, that little sharp piece right there, right? That little bit that's right there won't affect that bit. So then, like so. But now absolute value is going to affect everything else. So in particular, what's going to happen is if we just consider the blue for the moment, then what will happen is that all of that will be reflected up. So for example, that output is -1, and it's going to reflect to what? To +1. So like this. And then that output is -2, it reflects to +2. And then that's an open circle, so strictly speaking it's not anything, but at any rate it's at height -3, so it reflects to +3. So up to here. So that's what absolute value does to the blueness. Okay, so then now let's consider just the green. So we already considered that little sliver that's unchanged, right? But for example, that output is -2, and it reflects to what? +2. So specifically there, it'll be at 2. And then that output is -3, so it reflects to +3. And then that's an open circle, so strictly speaking, it's not anything, but at any rate, it's at height -2, so it reflects to +2. So can you connect the dots and see what it's saying? It says that the result will look like that. Okay. Finally, the red bit is the easiest bit, in fact. What becomes of it? Very good. So can you see what happened? Absolute value doesn't affect all of it, just the parts where the output was negative. Did you have a question about this? Good. Any questions about it? All right. Good. So that's concerning piecewise defined functions. Then the separate and second issue that struck me as we need to talk about this before the exam is a reminder about the integral. What integral is. But in fact, we talked about it one way, and some of y'all seem to pick up some of the concepts. That's good. So I'm going to try talking about it in a slightly different way and see if maybe I can pick up, changing the way I talk about it. Maybe we can pick up more. All right. So, all right. This is sort of calculus from the point of view of geometry, like from a hard view. So then, when we draw the reals, usually we draw them just as a horizontal line, and by the time you get to calculus, often the instructors will start taking the view, the strategy of only drawing one arrow. The reason is, there's a reason for it, and the thing still goes all the way that way, but I don't want to draw an arrow going that way. So if I want to signify that it continues going that way, then I'm going to draw an arrow that looks like this. So that means that it still is going that way. That's the meaning of that symbol. But I don't want to draw it pointing the other way because the pointiness is now going to be significant. The significance of it is that, the kinds of creatures that live in here are little one-dimensional arrows, because that's all that can fit. So specifically, consider this one-dimensional arrow. So that one right there. Suppose we get out our ruler, like a linear measuring device, I mean. Suppose that we get out our ruler, and we determine that this has length and I'm going to leave myself a pretty big horizontal gap there. I'm going to say length 3. So I left a horizontal gap there that I'm going to fill in a second. Okay. So that's one of the citizens of the real line. And then let's consider this one. So here's another one. So I've purposefully drawn it, slightly longer. And suppose we get out our ruler, and we determine that this is length. And again, I'm going to leave myself a gap, and write 4. A little bit longer than the red one. But here's the thing, is that what we want to do is we want to assign lengths to these, but we also want to have signed length, which means that we want to refer to one of these as having a positive value and the other one as having a negative value. So the way that we do it, the way that we signify it, is whether or not the pointiness is in agreement with the world. So the world is pointing to the right. So if you're in agreement with the world, then we're going to assign that value to be positive, which means that this length, we're going to refer to it as positive 3. Because we get out a ruler and then it measures 3, but also, in addition to that, it's pointing in the correct direction. Okay? So how are we going to refer to this one? negative, right? Because when we get out the ruler, you know, we get 4, but notice that it's pointing in the opposite direction. Okay, so fine. So that's positive because it agrees with this. And that's negative because it's in disagreement with that, which is why I'm not going to draw a left arrow going that way anymore. Okay, so then now, for 2, that is to say, R2. Instead of a one-dimensional world, now we have a two-dimensional world. So now the world looks like this. Where we have 2 axes. And we have to have a rigid convention now, because there's 2 axes. We have to decide which one is the first axis. So the convention that is universal is that the horizontal one is the first axis, and the vertical one is the second. So that means this one is considered first, and that one is considered second. So what that means is that just like the creatures that live in here are one-dimensional pieces, the creatures that live here are two-dimensional pieces. So they're little two-dimensional bits. So in particular, the way that they're constructed is by taking a one-dimensional creature from this one, and a two-dimensional creature from that one, and then just placing them anywhere that you want. So for example, here's a one-dimensional thingy. So suppose that we get out the ruler, and we decide that is 3. Okay. Do we need to say that that's a positive 3 or a negative 3? Just this red bit. Positive because it's in agreement. Okay. Similarly, suppose that from here, we do this one, and this turns out to be 4. And now that is a member of the second axis. So is that a positive 4 or a negative 4? It's a positive 4. So now from these 2 bits, from this one-dimensional thing that's a member of the first axis, and this one-dimensional thing that's a member of the second axis, we can construct this thing. So now the rule to figure out whether or not the result is positive is you draw this swirl. And the rule is that first you follow the piece that comes from the first axis, and then you follow the piece from the second axis. So this says go to the right and then go up, and now you have to come back. So now have a look. The world, if you follow first the flow of the first axis and then the flow of the second axis, it looks like this. So that's what positive looks like. As a result, this is positive. So that's positive. Okay. Now, what if we do the following? What if we say, here's a different piece. Oh, and by the way, the area of this is 3 times 4, and which is of course 12, but it's going to be positive 12 because it's in agreement with the world. Okay, fine. So now here's another rectangle. Suppose that we have that one-dimensional bit, and we also have say this. And again, suppose that we measure this to have length 3, and we measure this to have length 5. Ignoring the signs on the 3 and the 5 for just a moment. So let's draw the swirl. Okay, so the rule is that first you follow the first axis piece, and then you follow the second axis piece. So the swirl is going to look like this. So now, is that the same swirl or the opposite swirl from the world? It's the opposite. So this is what negative looks like, clockwise. This is what positive looks like, counterclockwise. All right. So then, as a result, the area of this, the area is 3 times 5, which is of course 15. But what sign are we going to assign to it? Negative. So here's a rectangle with area 12, positive 12, and here's a rectangle with area negative 15. Okay, good. Any question about this? So now this goes on, right? You can do this in 3 dimensions, and yes?
So I know you explained this before, and I understand it as you draw it, but tell me if I'm just like, just considering this, because I've ever looked at that just like geometrically without the arrows, I was just thinking, oh, they're both 12 and 15.
Okay, no dispute. But my claim to you is that that view is sort of the same thing as saying I can't really tell the difference between a bank account of that has $1 million in it or another one that's overdrawn $1 million. So is there a difference?
Yeah, I mean, just because because you're drawing 2 intersecting lines, like I'm looking at like a Cartesian plane, and they're in like the first, whatever the right hand one is, like you can.
Oh, this is not relevant. So I mean, we could transport this to anywhere that you like.
Okay, so we just dismiss the fact that it looks like that.
Yeah, it's not relevant. Their physical locations are not relevant. In the same kind of way that you're like 6'6", I don't know, in this room, but. Well, that's also going to be the case in the parking lot, right? Okay. Same idea is that even if we take this one and transport it over here, it's still going to swirl counterclockwise, even if we move it over here. Because over here, notice that down here, the first component is still going to the right. Okay. So now here's the thing: is that integral, what it does. Is integral is connected to the idea of area. Specifically, if this is y is f of x, and this here is the x-axis, which of course has a formula, y equals 0, equation y equals 0. Then the integral from a to b of f of x dx is the signed area between y equal f of x and y equal to 0. Now, what that means is that the area that the area that happens to be above the x-axis, that means that we're going to count that area as being positive. So specifically, what the way that we've been saying is that yeah, we'll figure out whatever that area is. That's part of what the integral will do. And as far as bookkeeping is concerned, that'll be accounted positively. And where bookkeeping is concerned, we'll also account for this area, but it will be accounted for negatively. Right? And we've done this several times. This kind of idea. Now, the convention of the reason for this is not like some genius a long time ago said, like decreed, and we're all just living by this genius's like a proclamation about how these things should work. It's not really true. So if you'll recall, the way the integral works is that integral from a to b the way it works is we said, okay, well, in the first place, what we'll do is we'll cut this into some pieces, and then we'll estimate with rectangles. So that's what we'll do. Now, to make things just sort of work out nice, the height of the rectangle, I'm going to take it to always be, I'm going to take it to be furthest to the right. So what I mean is that I'm going to consider this rectangle right here. And this rectangle, and this rectangle, and this rectangle. So specifically what I mean is that I'm going to consider this one, and that one, and that one, and that one. Okay? Now here's the thing. When we break up A to B, this interval, we broke it into these 4 pieces. But the way that we did things, kind of subtly, it might not have been entirely clear when we did it the first time. These pieces maintain the underlying orientation of the world, which means to say that notice that I drew that arrow going up, that right arrow going up, that one going up, that one going down because we had to go down, and that one going down. But before we did that, you know, we've got this little piece that goes to the right here. So like this, like this, like this, like this. So now the thing about area is it doesn't matter where you transport a shape to. That has no effect on its area. Right? So what I'm saying is that the integral, at least an estimate for the integral, you can obtain the estimate by considering each one of these separately. By saying, okay, well, I'll take these 4 separate pieces. 1, 2, 3, 4, and then I'll take them to my laboratory. To my measurement laboratory. And then I'll figure out the area of each one. Well, suppose that you know, I measure base and height, figure out the area, but I also need to figure out the sign of each one. So what would be the sign, ignoring the picture now, what's the sign of that area? Positive, right? Because counterclockwise, that's the same sense as the underlying space. So that's a positive area. That's a positive area. How about this one? Negative, because it's clockwise. Similarly, this one. The positivity and negativity doesn't really have anything to do with over or under. It has everything to do with swirly clockwise or swirly counterclockwise. That's what the real thing is. So now this is just an estimate, and in particular, the way that we define things. In the integral, we said that piece has size delta x, that piece has size delta x, that piece has size delta x, that piece has size delta x. When we were defining the integral, we referred to this to the sampling point, the place where the green arrow is anchored. Now, when we were actually defining it, it could be anchored anywhere, but I'm anchoring it at the right just for simplicity. We said that we called that point right there C1, we called that point right there C2, we called that point right there C3, and we called that point right there C4. And then how was it that we found the height? Well, we took that C1 and plugged it into F, right? We said that this was that has length F of C1. And then what is that one? F of C2, F of C3, F of C4. And then we take these 4 individual rectangles, take them back to our laboratory, find their areas, determine their signs, and then we add them all up, and that constitutes our estimate for the integral. So the way that we wrote that is we said summation from I is 1 to 4 of f of ci delta x. The product of those two, because that thing right there is the area of the ith rectangle, and what we're saying is add up all four areas. So that's our estimate. Now how could we make a better estimate? More rectangles, right? So instead of using 4, maybe 5. Instead of 5, maybe 5 million, you know? Whatever the problem demands. But what I want you to see here, what I want you to see is that every one of the rectangles, for every rectangle, you must evaluate f once. So what I mean is that for this particular drawing, because there's 4 rectangles, that means we have to evaluate little f 4 times. And if instead of 4 rectangles, if we wanted to use 8, we'd have to evaluate f 8 times. And if we wanted to use 1326 rectangles, then we'd have to evaluate little f 1326 times. Now, the definition of the integral is that it's sort of the imagination saying that, well, let's just let the number of rectangles become infinite. Let's just let it happen. Okay, well, integral, this thing, f of x dx. So in the first place, if we use the letter n to denote the number of rectangles, then I'm leaving myself a spot right there that I'm going to fill in just a second. So if we had exactly n rectangles, then it would be the summation from I is 1 to n being the number of rectangles, of f of ci delta x. Because this right here, that's the signed area of rectangle I, just that piece by itself. And then now we're saying that the sum of all of those, so now we're going to add all those up. So you cut it into n pieces, you find the area of each piece, you add them all up, and then to be an integral, the final math concept is what I need to write right there. So what is it that I need to write right there? It is, conceptually means, and let the number of rectangles become infinite. What do I have to write? I'm fishing for an L word. Limit, that one, right? So you've got to write limit as n goes to infinity. So that is saying let the number of rectangles become infinite. All right, so now let's consider this for a moment. Again, if we use 4 rectangles, that means 4 evaluations of little f. And if we used 44 rectangles, that would be 44 evaluations. And if we used 44 million, that would mean 44 million evaluations. What I want you to see is that what this concept is saying is it is, in a sense, requiring, therefore, this requires, in a certain sense, infinitely many evaluations of little f. Now, if that was the end of the story, then integral, we wouldn't even have this class. This class, in a sense, would be worthless, because this is, in principle, like not possible, right? You can't carry out, it's not at all clear what it would mean to carry out a procedure that has infinitely many steps. Okay? And what I mean is that, you know, if the story stopped here, we just wouldn't have this class. You know, there's plenty of interesting math that I know and love that, well, unless y'all become math majors, y'all are never going to meet. In the end, primarily, because it doesn't have any apparent use to society at large. Okay, I can accept that. And if this was the end of the story, we wouldn't even have a calculus class. Okay? But it's not the end of the story. The fundamental theorem of calculus says the following. It says, if, in the first place, the antiderivative of little f of x dx is big F of x plus a constant. Now, these two things look similar, but they're not the same thing. Okay? The antiderivative of a function is another function. The integral of a function is a number. Right? It's the assigned area. So they're not the same thing. If you know the antiderivative of little f, and furthermore, the integral from a to b of little f of x dx exists, that second thing is mostly a technical matter. It doesn't really come up very much in this class. So I'll just skip it. Then, here's the thing, is that the integral from a to b of little f of x dx, which we just discussed, what it does is it takes the shape in question, cuts it into little oriented rectangles that have either a positive area or a negative area, and then adds them all up unless the number of rectangles become infinite. This thing over here requires infinitely many evaluations of little f. That's what this one requires to do. The fundamental theorem of calculus is saying that, in fact, this is equal to big F of x evaluated from a to b. And of course, the evaluation bar is just a nice notation, which means what? So what does that mean? It means big F at b minus big F at a. That's what that means. So now, here's the thing, is that how many times, just looking at that, just that part right there, how many times did we have to plug into a function? Twice. And looking at it this way, to carry this out, how many times do we have to plug into a function? Infinitely many times. Now, is there a contradiction here? No, it's not, because look at this one is saying. This one requires infinitely many evaluations of little f, but this one just requires two evaluations. Two evaluations of what? Of big F, not little f, right? Of its antiderivative. So this is two evaluations of big F. So what's happening is that the fundamental theorem of calculus is saying that, well, you can either evaluate that one infinitely many times, or you can evaluate that one twice. But you're changing it, you're trading. And they have to be connected through this, right? These aren't just any old little f and big F. It's ones that do this. Okay? So now, that being said, I'm going to give myself an exercise and then solve it incorrectly, and I want you to speculate as to what might have gone wrong. So again, I'm not really speculating. You know, what I am doing here is, you know, I graded your papers last week, and I saw a response that looked more or less like this. So here's a question. You know, the statement is just evaluate this. All right. So I'm going to do the following. And again, this is you know, a serious mistake. So you know, if you're copying what I'm writing down, understand that it's not correct. Okay, so then here we go. Okay, I remember this kind of exercise. So what you do is you do this, 4 times x minus 5, and then you do it like that, 1 to 3, like so. And then now I plug in the stuff. So that'd be 4 times 3 minus 5, and then subtract 4 times 1 minus 5. So that would be 12 minus 5 is 7, and then subtract negative 1. So that would be 8. So is that right? No. Now, but wait a minute, I did the arithmetic right? Right? Yeah. What went wrong? Right. Let's consider. The FTC says the following. Fundamental Theorem of Calculus says that, you know, looking at the definition on the previous page and just copying the punchline, the integral from a to b of little f of x dx is its antiderivative evaluated, boundary evaluated from a to b. That's the FTC. So now, in the question, what is little f in the question? Well, it's 4x minus 5, right? That's what's playing the role of little f. So this is little f. Okay, so now you tell me, what mistake is it that student has made? Right. Just copied this little f here again. So let me sort of explain to you why this is such a serious problem. See, the thing is that the fundamental theorem of calculus, what it's saying is that, more or less, you can trade infinitely many evaluations of this function for 2 evaluations of that function. And that's incredible. That's an incredible savings. But what this response is saying, it's saying that, nah, I'll just use little f. See? So can you see the problem? So to make this right, just so that we have a correct answer on the page, 4x minus 5 dx, like so. What is the antiderivative of 4x minus 5? Very good. And then 1 to 3. So this is correct. Okay, so then what I want to stress is that in the first place, what I wrote up here, this is not right, but it's not right in like a big way. It's not right in the same kind of way that, you know, if you have any children or if you've been around young relatives, and, you know, babies like bananas. That's just like, I think that's pretty much universal. What if you saw your child or someone that was otherwise dear to you, and they picked up a banana-looking thing and then took a big old bite of it, but it was actually made out of like styrofoam. It wasn't a real banana, and they just kept eating it. Right? That would be like really concerning. Like I would claim that that's more or less like a child has not yet understood that there's a big difference between you know the food concept. That's kind of what this is like. This is this kind of mistake is wrong like in a very serious way. So nothing else but a 0 could come of this error. Good. So any question about the idea? All right. Last thing is now I want to combine these two concepts. Is that suppose that we have a piecewise defined function, and furthermore, we want to use the fundamental theorem. So that, well, suppose that we have something like the following. Let h of t be given by something like I don't know. Okay. T plus 2 when t is less than, say, 1, and something like -4 otherwise. So the first request is please sketch the area, and of course by that I mean the signed area. Sketch the signed area. What am I trying to say? Sketch the signed area, which is related to, I'll say defined by, I guess. Kind of at a loss for words. Defined by integral from -3 to 5 of h of t dt. So that's the first request, and this will be like part A. So part A, part 1, do that, and then 2, evaluate that same integral, -3 to 5, h of t dt, with geometry. That is to say, just using little formulas there. And then 3, do the same thing, but with the FTC. All right? Good. So again, taking the same strategy, referring to these, this piecewise defined function, the clauses top to bottom starting at 1. One good element of strategy is to more or less kind of follow what we did before, which is to say, let's find the domain, let's find where everything joins, and let's get a general idea of what behavior is expected in each piece. Okay, so then this is just the general idea here for a sketch. So what join points are there? Okay, so -4 is not one of the join points. Why is it not one of the join points? I can see the -4 there, but why is it not among the joins? Well, I agree, but in the end, it's these pieces. These are the ones that determine which formula is going to be used. So that's a formula, but that's the rule that decides whether or not you're going to use it. So the only join is at 1. At t is 1 here. And then which clause holds sway to the left of 1? The first one, right? And which clause to the right? The second one? Now, if you were to plot, you know, if that was the formula for the function, h of t is t plus 2, then what would the formula what would the world look like to you? What would the plot look like? It'd be a line. Okay, so and it would be sloping up. So again, not trying to get it perfect, just the general idea. This is some line that slopes up. And then when it comes to the join, does it join open or does it join closed? Open. So like so. Good. And then to the right, what kind of thing, if that were the only formula right there, h of t is -4, then what would the plot look like? It'd be a horizontal line. So a horizontal line. And then when it hits the join, does it join open or closed? Closed, right? Because the reason why it's closed is because, well, what if you were to plug in 1? T is 1. So can you plug in T is 1 to the first clause? No, because 1 less than 1 is false. That one means, more or less, that if nothing above was true, then this is the catch-all, right? This is where everything goes. So that one wasn't true. As a result, we're going to use this one. So it's included, which is to say that if we wanted to evaluate h of 1, then we would do so with clause 2, and we would get -4. So it joins with a closed circle, like so. So now to make, this is not a sketch, this is just to illustrate that the function in question sort of has two phases of life. One where it has the red behavior, and then the other one where it has the green behavior. So it's going to look kind of like that. Now, let's give it a good sketch there. No, but I mean, if on the exercise I want you to sketch something, I just give you, I give you one. You know what I mean? Like, it's just printed there. That's if I want like a nice looking one. Otherwise, if I just say sketch and don't give you one, I don't expect it to be like an artist. But it needs to be like, pretty good. But not perfect by any means. Okay, so then I can see that there's a join at 1. Okay, so that's at t is 1. And then now we want to do some plotting. So now for the green part, I can see that the output should be always at height -4. So 1, 2, 3, 4. So closed, blah, blah, blah. So like this. So that's what that looks like. All right. And then, okay. So then, going the other way. Let's plug in some points that we can plug in. So for example, we can plug in 0. So what do you get? This is a line of slope 1 and y-intercept 2, right? So then this point has got to be there. And so we can proceed to the left like this. So now, at the cost of repeating myself and being overbearing, I will nevertheless repeat myself. Is there something wrong here? Okay, I agree. What?
There's, space.
Yeah, right? Presently, there's like this gap. Okay, so this sketch is really not right. This is saying, at least as it's currently drawn, that it's not possible to, for example, plug in half, because you don't get a green value, and you don't get a red value. But that's, in fact, not true, right? At half, we should get a red value, which is to say that this must continue up to here. Okay, good. So now, still, this is not quite finished, because what we were interested in is we were interested in the area defined by that, the signed area defined by that integral. So what else need we plot? Yeah, we need to do -3, input -3, and input 5 also. So 1, 2, 3. And also at 5, so that's 5 there. 1, 2, 3, 4, no, that's 5 right there. Okay, so 5 right there. Okay, so then what does that have to do with the question then? Because it's still not quite complete. So it's not, it's the way what's currently drawn, it's not clear to me, like if I was to see a student submit this as an answer to this question, it's not clear to me that student understands what area it is that we're referring to. So specifically I need you to like shade in or something, the area that we're talking about. So what area is it that we're talking about? Right, because you know, this is the t-axis, and if we say that what we're plotting is like you know, I don't know, what kind of output? What would you name the output there? If the input is t, how about u? If we're going to plot u is h of t, and call that u, then this thing right here is the line. Whoops. Is the line u equal to 0. That's what that one is. This one is the line, that just the green bit, is u equal to -4. And just the red is u equal to t plus 2. So what we want is the area that is between the red and that one, and also the green in that one. So it's kind of, does that show up on the screen? Okay, so furthermore, you know, this would be sufficient for the answer, but let's make sure that you know, test our understanding. You know, visually, there's kind of like 3 pieces, 1, 2, 3. Which one will are counted negatively? Correct. So as it happens, the ones that are beneath u equal to 0. Now the reason for that is, you know, you can just remember, you know, you can kind of like remember little rules or whatever. But the reason is because when the way it works is that when you were making rectangles, first we go to the right, and then we go down to get to the green one. And that causes a clockwise swirl. That's why this one is negative. This one is first we go to the right, and then we go up. And that causes a counterclockwise swirl. Okay, whatever. So negative bits, positive bits. Okay? Therefore, the integral from, what was it, -3 to 5 of h of t dt will be this little bit, but we're going to count it negatively, right? That little bit there. And then we're going to add to that this thing. And we're going to count it positively. And then we're going to add to it this other piece, but we're going to count it negatively. So the area of that one, but negative. The area of that one taken to be positive, and the area of that one taken to be negative. All right? So that means we need to measure the little bits there. So measuring, that would be, no, that would be 1 by 1. So that would be base times height over 2, but negative. And then plus that. So this would be, this one is 3, so this would be 3 and 3. So that would be plus base times height over 2. And then, well, minus, I guess, is the way I'll write it. And then that would be 4 and 4. Okay, well, like so. And then, you know, you can do the arithmetic from there. Okay, what would it be? It would be a... Ah, no, you don't. You don't divide. That's not a triangle. Thank you. So that would be 9 halves minus 1 half is 8 halves. So that's 4. And then minus 16. So that'd be negative 12. So now, just using like the sniff test, the reasonableness test, does it seem reasonable that the answer is negative? Well, we're sketching the signed area, right? I'm not asking for the area of the shaded region. I'm not asking for that positive, and that positive. I'm asking just for the integral. So does that seem reasonable that the answer should be negative? I think so. Can you put it into your words?
Because there's more negative area than positive.
It appears to me to be that way. It appears to me that there is more below than there is above. So, like, you know, you're making profit some of the time, you're making losses some of the time. But it appears to me that the losses exceed the profits. So altogether, you're losing money.
So in this case, it's okay for area.
Right. Okay. So now, what if we consider part B? Oh, we're just about out of time. So part B, I want to do the same thing, but more or less. But I want to do it with U is the absolute value of h of t. So I'm going to just do this really quick, because we just have a few moments here. So how would this be similar, and how would it be different? So it would be similar in that, you know, we did something like this an hour ago or something. So it's going to be quite similar to this one. We're still going to have these joins, those places right there. So I'll plot those real quick. So -3. And 1, 1. And 1 here. And 5. But besides those points, what else is significant? There's one other point that is significant. -2. So you're saying that's important? Why is that one important? Right, that's the place where in a sense the action of the absolute value is going to be most apparent. So that's important too. As a result, you know, it'll look like that, going that way. like that. And now, assuming the same instructions as the previous one, this is the area. And if you wanted to find the formula, then it would be these individual terms, except taking all of them to be positive. So now it would be positive half plus 9 halves, so that'd be 10 halves, so that'd be 5, and then plus 16, so it'd be 21. So that's 21. Finally, and this is the very last thing. As a reminder, the new questions on the midterm, they're going to be new, right? And someone had asked in the other section, what's an example of something that might be on there? So they heard an example, so I want to make sure that you all hear that same example. So here's an example. I could say something like, let f of x be equal to some specific thing, like, I don't know, 3x squared minus 5x plus 8, I don't know. And then let g of x be the tangent line to f of x at the specific point, just, you know, I don't know, I haven't thought about it deeply, at x equal to 2, say. So that's f, that's g, and then I could say find the integral, say, from, I don't know, negative 3 to positive 4 of g of x dx. So now, I'm not going to solve this, but rather I want to explain to you what this question is doing from a teaching point of view. So now, I gave you a formula for f. That's f's formula, right there. Did I give you a formula for g? No. So that means that before you get started on this exercise, that means that you have got to figure out the formula for g. You've got to figure it out, and it's only after that that you go on to do this other concept. So the purpose of this kind of question is that I'm on all of the WEXs that you've done for like quizzes and homeworks. The intention was more or less to test a single concept, like just one question, one concept. For the midterm, more or less what I do is I just select 2 concepts, and then I just brainstorm a new question that uses those 2 concepts. So here, conceptually, what's happening is this, is that, you know, again, this is just the generalist sketch of what's going on here. I make no claim that this is how it actually appears. But what I've given you is I said, you know, I gave you that thing. That's a parabola that opens up. So it looks something like this. You know, and what that is that's y is f of x. And then I asked you to compute an integral. So is it the area under that curve that I'm asking for? No, right? It's not that. It's not that because what I did is I said, no, actually I want you to integrate g. So what you've got to do is say, oh, okay, well, there's an input in here at 2, you know, about, say, you know, just for the purposes of the picture, I'll put it right here. Only, you know, I know it's not really right there, but let's imagine. X is 2. Well, somehow, you've got to come up with the formula for the tangent line right there. And it's going to look like this, somehow, you know, something like this. So that's the formula, or that's the plot for y is g of x. And then it's that green one that I want you to integrate. Does everybody get it? So like I give you the red function, and I describe to you how to get the green one. and then I want you to integrate the green one. So what happens is, well, I'll just forewarn you, is that if I were to ask such a question, then I expect, you know, a certain percentage of students to just integrate the red one. And if that happens, then you won't receive credit for that, because you've not followed the instructions, essentially. Any question about this kind of thing? Yeah?
For the sake of the test, Midterm, if you ask for the shaded region of some shape, that's absolute value, but if at any point it mentions integral, then we just take them for the signs that they are.
Right. So if I'm saying integral, integral is always accumulating signed area.
Okay. If it only says shaded, then.
Yeah, if it says consider the region and shade it in and then find the area, then that means I want you to do it. I want you to do it as if the individual pieces all have positive value.
Okay.
Yeah.
And the answer must be positive.
In that case, yeah. Yeah. Good. So that's what the new ones on the midterm are. The purpose is that I more or less select two concepts and then test them. And you know, you'll see them the first time on the midterm, right? But then on the final, there will be redo versions of those as well. So, you know, it's not like, I mean, study, you know, understand. But, you know, don't be deflated entirely, is what I mean. You know, don't, panic. Yeah. All right. So I hope you have a wonderful Tuesday.